So what did we talk about last time? I drew two kinds of figures, and what did that help us think through?
Stable and unstable.
Stable and unstable steady states. And right when we got close to the steady states, we kind of knew what was happening. Why is that? Which is sort of the tail end of last week. Yeah, so as we got close, we could do a Taylor series in the neighborhood of the steady state, and then we could think about whether it had a positive feedback or a negative feedback, and then we knew how that system works already because we solved it for the general case last week, even though we didn't realize how important it would be until we started drawing these pictures. And the pictures allow us to go farther away and kind of imagine what happens in between the steady states. Not quantitatively, we're not solving for the speed that you might traverse that space out in the middle. We'd have to solve the nonlinear differential equation to do that. But qualitatively, like over this whole range of possible x values, it's always going that direction, so it's going to end up falling into that steady state. So the basic gist of our system was that we were thinking of things that were like this, where we said our time derivative of x, or whatever, our one independent variable derivative of x was some function of x depending on parameters. Then we had a second kind of graph. What was that one? That had the parameters as one axis. Bifurcation. There we go. There we go. Yeah. So the bifurcation diagram allowed us to think about how the number of steady states changes, and maybe their stability changes as we go from place to place in parameter space. And so the combination of this allows us to start thinking about how these different systems work. So all the ones we wrote down last time were all one dependent variable, so one-dimensional flow, if you like. Today we want to talk about two-dimensional situations. And so the difficulty is that our graphical approach in 1D isn't going to work anymore because we can't draw a four-dimensional phase space plot because we only live in 3 dimensions. But we would like to think about how we can still use those same insights of like mapping out the space and thinking about regions of behavior which all are qualitatively similar, and maybe think about how we might think about a bifurcation diagram in the higher dimensional system as well. Okay? So we actually have already studied a 2D flow, even though we might not have thought of it that way, because we studied a second order differential equation for our displacement in the Brunt-Weissela frequency case. Remember, this is the one where we have a stratification, so we have pressure increasing as we go down, and we had density increasing as we go down, and we took a little blob and we displaced it, oops, and then it oscillated. Remember that problem we did in the last week in the ODEs? It was our simplest second order ODE equation, and remember it was the one that we got interested in the fact that there were imaginary M values in our assumed solution form. And how do we solve this? Do I remember? Or what kind of equation is it? If n squared is constant?
Homogeneous.
Homogeneous, linear, constant coefficient, second order differential equation. And so we basically wrote down this, and then we did some work and found that m equals minus, or I, oops, got me right, I times n. And so instead of being an exponential decay or an exponential growth, it was an oscillator, right? Does everybody remember how this went? Everybody, this seems slightly familiar. Maybe I'm forgetting what I've talked about and what we haven't. One of the terrible things about teaching a class multiple times is you'll be like, I keep saying this the same way, and you guys just aren't learning it. But what I'm really remembering is that I taught it like in previous versions of this class to other students. So sorry if I have not actually said this before, but I think we did do this at the end of last week. Okay. So this is a second order because there are two derivatives. But last time I suggested that we might consider this as two first order equations. Does anybody remember how that goes? How can I write two first order equations that look like this and have the same information content as this equation? I'm giving it V here to be suggestive of something.
Are you talking about this is what we did at the beginning on Monday?
Yeah.
So we did p dot equals f of x and x dot at r.
Yeah.
Something like that?
Yeah. So in this case, so what are I could talk about the displacement, or I could talk about the time derivative of the displacement. What's the time derivative of the displacement? The what? The velocity. As it goes up and down, it's got both a position and a velocity. So like, whatever, high school physics. I could just say my time derivative of delta z is a velocity, and then I can talk about an equation for what the time derivative of the velocity is. But that's what this is. This is the second derivative with time of the displacement, or it's the first derivative of the velocity. So I write this as minus n squared delta z. So this is the same system as this equation, exactly the same. I've just introduced a new variable, v, which is the velocity. And now look, I've got two first order ordinary differential equations instead of one second order ordinary differential equation. You can always do this. You can always break them down into first orders by introducing new variables that are like the intermediate derivatives. Now, there's a complication. I can't solve this equation without knowing the solution to this equation, and I can't solve this equation without knowing the solution to this equation, because this thing depends on this, which is in that equation, and this thing depends on this, which is in that equation. So they are coupled first order differential equations. So I, in general, can take higher order ordinary differential equations that are uncoupled, just a single equation, and produce a set of coupled first order differential equations. Okay? So coupled means I have to solve them at the same time. I need information from both of them to move ahead. Okay? So if I was going to code this up in MATLAB, or Fortran, or whatever you want to solve it, I would say, okay, let's guess an initial value for delta z, let's guess an initial value for v. Let's evaluate this side and talk about what the rate of change of those two things would be, and then I'll move forward one time step, and everybody will update, and then I'll do it again. Does that make sense? But I could do it. It's just complicated because I have to know all the different variables all at the same time to take that time step. Okay? So we're going to try and do the same thing schematically in this kind of flow that we did before. So if I make a diagram where I put delta z on this axis and v on this axis, this is sort of like, remember last time we were putting x on this axis and x dot on this axis. And then we went along on the, and found our steady states along the x axis, and then we were paying attention to the derivatives everywhere. Does that make, remember how that went? So now we're doing the same thing, except the derivative axis is just in our brain. So we're going to try and walk along the x-axis and map the steady states here, and then we're going to use our reading of these equations and brain to have the other dimension that's now only in our brain for this. Does that make sense? So we're going to try and draw the arrows the same way we did before. So if I had like, you know, steady state here and here, then we were drawing little arrows that go like this. We're going to do those arrows, but we're going to do it by just thinking our way through what the information on that axis would be by looking at the equations rather than drawing them. Because we can't draw the four-dimensional phase space diagram. We're just drawing the 2D phase space diagram. Does everybody understand what I'm trying to get at? So is there a steady state solution here? Yeah, because this is a homogeneous system. So if V is 0, then this is 0, and if delta Z is 0, this is 0, and this is 0, and this is 0. So there's a fixed point. We don't totally know that that's the only one. Turns out that is the only one. But you have to think a little harder to be sure that you haven't missed something. So what happens out here somewhere else? What if we just try a point? What if I take my initial condition here? So that means that V is positive, delta Z is 0. So if delta Z is 0, what is V dot? 0. If V is positive, what's delta Z dot? It's positive. So which way do I draw my arrow? Where am I going? I'm sitting at this point. This is positive and this is 0. So which way do I go? That way. Okay, what about here? Sitting, I've got delta Z is positive, V is 0. So V is 0, so what's delta Z dot? 0. And delta Z is positive, so what's V dot? Negative. Okay, what if I go here? Now I'm at V is negative, delta Z is 0, V is negative, so what's delta Z dot? Negative. Oh, sorry, I jumped over one. Delta Z is 0, so V dot is negative, so I'm going horizontally here. If I do this one, I go horizontally here. If I do something in here, I'm going to be something in between. Before long, you're like, hey, I'm going around in circles. And if I'd started farther away, I'd be going around in a different circle. If I was going closer, I'd be going around in a different circle. But we already knew that, because that's all this is. This is, you know, if I write this out, this is delta Z equals delta Z naught cosine nt plus I times delta Z naught sine of nt. And then you're like, oh, what does that mean? What's the I about? But the time derivative of this would say that delta Z dot is, oops, I need an I in there. Oh, no, I didn't need an I in there. That's right. So if I take the time derivative, the I comes out front, and that makes this one imaginary. Cosine nt. And this one is now real, minus delta Z naught times n sine of nt. So I've got something that in the delta Z world, this is equal to V, it's going around like cosine. So I'm going back and forth, oscillating in delta Z axis. And delta Z dot, or V, is going like sine. Back and forth and back and forth. And the imaginary part is just helping us keep track of the imaginary thing, but it actually doesn't affect the value of the real part of delta Z, or the real part of V, which is what we are really interested in. Everybody following what I mean? So we could have guessed that it was circles, because this never collapses back to the origin. It always just goes loop-de-loop-de-loop around and around and around. It doesn't have an e to the, if it had, e to the minus RT multiplied by that, then it would do what? It would spiral inward as it was going around. Or if I had a plus R, it would spiral outward as I was going around. And it turns out that's it. Those are the only possibilities in 2D. When we're near a fixed point, and we do a Taylor series style expansion, so we linearize this equation, we can have circles, we can go in, we can go out, and we can combine those things so we can have spirals in and spirals out. Yeah.
Can you go back to when you were drawing it?
Yeah.
The point that's on the v-axis, but positive. Sorry. Yeah.
This one?
Yeah. So delta z is 0.
Delta z is 0.
Doesn't that mean that v is 0?
No, it means that v dot is 0. So v dot is the time derivative. Remember, this is d by dt of v.
Then how did we say that it was positive?
So if this is 0, then v dot is 0, which means that my arrow doesn't have any component in the v direction. It's just flat.
But how did we know which way?
Oh, because then I said v is positive, which means that delta z dot is positive, so it goes towards positive delta z in the next instant. And this one is the same, except now v is negative, so delta v dot is negative. So basically, we did the same game we were playing over here, but we had the added assistance of like drawing, I do it right. Over here, I can't, the one I drew is not possible, is it? Oh, yeah, it is. Here, we were plotting the x dot on top of it, and so we were using that to help us remember which way things go. So when the graph was above, we were going that direction. When the graph was below, we were going that direction, or that direction. So we're just doing that part of it in our brain over here. I go to this location, and then I'm evaluating the dots. I don't plot these functions. I just evaluate them at that point and then draw an arrow to reflect the way I go. Does that make sense? I could have also drawn this figure too, a figure there, but it would have been 4D, so it gets complicated. So it's just like we're going through the same thought process. Because here, once we drew that figure, it wasn't that important. We could actually have done it without drawing the figure. Because all we need to know is it going towards positive x or going towards negative x? And here we're doing the same thing, except is it going towards positive z, delta z, towards negative delta z, towards positive v, towards negative v. Everybody on board? Sort of? Okay. And so then, okay, so I told you that we could only go around or go inwards or spiral outwards. That was the only possibilities. In the notes, I actually show you how to do that in all general detail. So it's a little complicated. How many examples do I do? A lot. But anyway, let's map it out a little bit and just think our way through it. Maybe without all the bits and pieces. X dot equals A x minus steady state. Make sure I get the numbers. C x minus steady state. D y minus steady state. B y minus steady state. Okay. So I claim that if we Taylor series approximate near any steady state, which has an x location and a y location, we're always going to find this coupled set of two first order constant coefficient linear differential equation. So this is, remember when we did the planetary energy balance one, we had temperature equals, or we actually wrote it as d by dt of temperature minus temperature star equals the feedback parameter times temperature minus temperature star. Right? That was the one we had there. This is the same thing, except now I've got to keep track of both x's and y's. I've got two different dimensions to keep track of. So in this case, our delta z was our x and our b was our y, and we found that we didn't. So which of these did we have in this system? What's a equal to?
B.
0? Yeah. And then what's b equal to? Maybe it's right at the intermediate value. So our lookup table is delta z is equal to, let's call that one x. V is equal to y. Delta z steady state is what? Where's our steady state solution here? It's at 0. So both of these are zeros. Okay, so delta z dot equals v, which is this one, not the same one, the other one. So this is b is 1, b equals 1, a equals 0. What's c? This one? Is that?
What are x and y?
Right here, sorry. Delta z is x, just like we plotted it. V is y, just like we plotted it. So this is the v dot equation. And I'm looking for the coefficient of delta z minus delta z star. The delta z star is 0. So what's the coefficient of delta z? Negative n squared. And then d is 0. Okay? So this is just written in a way that's convenient. If we'd done any Taylor series around a fixed point, we always would have gotten this. Right? And this looks an awful lot like our multivariate Taylor series because it is our multivariate Taylor series. And we could also, if we really want to go hardcore, we could write this as a matrix equation. Where M is A, B, C, D. And anytime, so this is nice, because now our matrix equation, we actually know how to solve an equation like this to some extent. We solved an equation like this. Does anybody remember how we did that? And now we just put a different derivative. So in the linear algebra system, we solved a lot of equations like this. And now we put a derivative into the game, which makes it a little bit more fun. But is a derivative a linear operator? So we can just, this is just part of our linear algebra system. You may remember how we did it. Involved diagonalizing, yeah.
It wasn't just like the eigenproblem thing.
Yeah, this is the eigenproblem, because we have the same beast on both sides. And so what we really like to think about is the eigenvalues of this matrix and the eigenvectors of this matrix. But maybe to be a little more explicit, the way I do it in the notes is this is the eigenvalue problem, where this is the matrix whose columns are the eigenvectors. This is the diagonal matrix, which has the eigenvalues on its axis. The zeros there. This is the eigenvector. And this is the inverse of that matrix. The inverse? So I can always write a rectangular matrix in an eigenvalue decomposition like this. But that's awesome because we can think about just this system. So d by dt x y equals c b c inverse x y. Alright, I'd like this c to be on the other side for a reason I'll tell you in a second. So I'm going to put c inverse over here. Right now I'm just messing with matrices. And we actually, for the A, B, C, D matrix, you can go back to the linear algebra chapter and just look up what these lambdas are. Like we wrote them down what they are in general for an A, B, C, D matrix, right? So we got them already, so we don't have to worry about them again. Okay? So what is multiplying this thing? Can I bring the matrix inside of the d by dt? And switch the order of those. So what are all these things in a matrix when I'm multiplying here? What's in the matrix? They're just constants, right? And so this is some elaborate procedure where I'm going to take constants times x and constants times y, or constants times d by dt of x and constants times d by dt of y. It's some elaborate linear combination of them, but that's all it is. So if I differentiate that before and I differentiate that after multiplying by constants, it's the same answer, right? I'm just exploiting the linearity of the derivative operator. So I can write it like this. D inverse x1. Okay, now look at the things I'm circling. They're the same. Let me see that. So what does that mean? I have something that's a combination of x's and y's. When I take its time derivative, I get a diagonal matrix times that same combination. So that means I have just uncoupled the two coupled equations. I don't know what, right now I don't know what c inverse of x and y is, so we could figure it out quickly with the stuff in, but if I call that p and q, whatever they are, which is some linear function of x's and y's, I now have a set of differential equations that looks like this. P dot equals lambda 1 times p. Q dot equals lambda 2 times q. I can solve those. What's the answer? P equals a e to the lambda 1 t. Q equals b e to the lambda 2 t. Done. From here to here. So let's write out what c and c inverse are. That might be way more concrete. Do I have it written down here? And I don't have the linear algebra. Does anybody have chapter 3, the linear algebra chapter? All right. Well, let's just imagine that C has 4 elements. This is C inverse. 2, 1, 1, 2, 2, 2. And whatever they are, that equals C inverse. So whatever these are, they're just constants. They're combinations of A and B and C and D from those original equations. They're selected so that this is one of the eigenvectors and this is the other eigenvector. And D is built out of the 2 eigenvalues, right? So we have the formulas in chapter 3 for these. So if I gave you a particular value for A, B, and C, and D, you could write this out for me, right? Like, you could just go through that procedure. But if I multiply this times x and y, then I find C inverse x and y is equal to C11 times x plus C21 times y, C12 times x plus C22 times y. And these are just constants. They're complicated, but they're constants. And now I'm just saying define whatever the answer of that is. It's some linear combination of bits of x and bits of y. I'm going to call that P. I'm going to call the other one Q. And when I write down the equation for P and Q, it's just going to be an uncoupled ordinary differential equation because it'll just be one of the eigenvalues is the only thing that sits in D. So this is the procedure for pulling apart those two equations in general. Yeah?
But doesn't P still depend on X and Y?
P does depend on X and Y. So we take this solution, and then we say, okay, now I know how P behaves. And now I know how Q behaves. Now we go backwards and we say, well, how did X behave and Y behave? X has some part of its behavior described by P, and some part of its behavior described by Q. Y has some part of its behavior described by P, and some part of its behavior described by Q, but it's a known linear combination of those things. Does that make sense? So it's difficult to solve for X and Y because we have to know the value of Y to solve the equation for X. We have to know the value for X to solve the equation for Y. But in P and Q, I can solve them. Just write them down, and then all I have to do is find out what A and B are in terms of the initial X's and initial Y's. And then I can go forward again and fill it all back in. So let's do one of these and see how it goes. I'll leave that part up so we can point it back at it again. This is a system which has two real eigenvalues, so it's not the system we just talked about. So x dot y dot equals 1, 4, 1, minus 2 times x and y. Okay, so that's horrible. It's coupled. It's nasty, right? Two coupled first order. Are they homogeneous differential equations? Yes, no, maybe. If I set x to 0, this one goes away. If I set y to 0, this one goes away. So this side is homogeneous. Over here, if I set x to 0 and y to 0, does the whole thing go away? Yeah, so it is homogeneous. But it's only homogeneous in both. You can't do just one without the other. You gotta squash the whole thing. So it is still homogeneous, but it's homogeneous in couple. But it's still a homogeneous system. We still could guess we could do a guess and check solution. So let's do a guess and check solution. Oh, well, we know what x, so since it's homogeneous, what's our steady state solution? Both zeros. Makes our life easy. If we had added another term over here that was non-constant, it would have been hard work, but we could have inverted this matrix and found the steady state solutions that kill it off. Okay, but this one is homogeneous, so we don't have to worry about that. So we can write right off the bat. Exponential solution, which in this case is actually just x and y, these two are 0. Okay, so we're just following our guess and check. First we checked it was homogeneous, it is homogeneous, now we're plugging in. But the problem is that we're going to have more than one M. We're going to have a couple of different things. So let's go the rest of the way through and figure out how, first we need to decouple this system. Oh my God, do I just do it the long way? Or do you just do it the long way? Right. Okay, if I assume this form for x and y, this thing, what's x dot and y dot?
How is C related to X and Y?
How is which?
T.
T. Oh, so this is time. This is what we're taking the derivative with respect to. Yeah.
Isn't it just like the one for 1 - 2 times AB?
So I could do it with this one. I could just rewrite that part. But what if this is the solution form? So we're doing our guess and check solution. So how do I get the time derivative of x and the time derivative of y out of this assumed answer? This is a constant, right? This is a constant. How do I take the time derivative of e to the mt?
Multiply by M.
It's just m times that. So that's going to be equal to a b times m e to the mt. So let's plug this into there and see what we get. That's going to be equal to 1, 1, 4, minus 2. Now what's x and y? That's just this. A, B, e to the mt. Everybody following? Sort of. So this is easy to solve if this matrix wasn't in the way. But the matrix is in the way. But is it a differential equation anymore now that I've gotten to this part? No, because in my guessed solution, I can just pull the time part out. So I can cancel this with this, because it's multiplying by a scalar. Now the t's are gone. And I have an equation instead. It just looks like this. A, B, M equals 1, 1, 4, minus 2 times A and B. Okay, so it's just straight up linear algebra now. Which kind of linear algebra do we need to solve that equation? We have to do an eigenvalue problem because it's got A and B on both sides of the equation. This is a homogeneous, not only a homogeneous differential equation, we now have a homogeneous algebraic equation that's sitting inside. So we could do Kramer's rule. Remember how to do that one? Because if I set A and B to 0, I set it to 0 on this side. So there's a trivial solution which says all you got is your steady state. You don't have any time dependence. Just crash into your steady state and forget about the problem. But that's not interesting. We want the homogeneous solution. And remember what I said way back when in the linear system, it's going to be really important when we use Kramer's rule because that's going to be all of the free oscillations of the system. That's what we mean right here. It's the deviations away from our steady state. Okay, so how do we use Kramer's rule? How does the thought process go? I can come up with a non-trivial solution to this system only if what happens? If I can invert this matrix, or actually let me rewrite it a little. 0 equals, I could have written this as the identity matrix times M, right? Everybody follow that? That's the same as multiplying by a scalar. So I can now subtract these two, and I've got 1 minus M, 1, 4, minus 2 minus M, A, and B. Okay. That's the same as this. That's just rewriting it, right? Everybody's on board with that. If I can invert this matrix, then what are A and B equal to? 0. Because if I can invert it, then it's 0 times a matrix. It's still 0. A and B are 0. That's not the solution I want. So I want to not be able to invert this matrix. So what do I check to see that means I can't invert the matrix? The determinant has to be 0. If it's 0, then I can't invert this matrix, and then A and B could be non-zero. So what's the determinant? 1 minus m minus 2 minus m times minus 4 equals my determinant, which I want to set to 0. Everybody got that? I just did this one times this one minus this one times this one. Okay, so divvy this out, what do I get? I get minus 2 plus 2m plus m squared. I missed one. Minus 2 minus 2m minus m minus 4 equals 0, which is m squared. That's this one plus 2m minus m minus 2 minus 4 minus 6 equals 0. So what kind of equation is that? So what I've got all kinds of sign errors because I just looked at my notes and I have 2 different answers.
I think it's plus m.
1 minus 2 minus m minus 4. That one's right. This one has got to be totally wrong because this is supposed to be plus and that's supposed to be plus.
I think it's still minus 6, but plus m.
Alright, hold on. This one is right. So let's do that more slowly. Okay, the first one is minus 2. The inner one is plus 2m. The outer one is minus m.
Shouldn't it just be negative 6? Because negative 2, negative 4.
Negative 2 and negative 4. Yeah, I think I have it wrong in the notes. That should be negative 6. And this should be plus. Okay, that's right. So the notes are wrong. Ha. But nonetheless, what kind of equation is that? Quadratic. And I can write down the solution for it. And what does the solution look like? I want to erase all of my magic over here. M equals what? Opposite of B, so minus 1 plus or minus the square root b squared minus 4 times a times c, which is 24, over 2 times a, which is 2. So this is minus 1 plus or minus 5 over 2. So it's either equal to 2 or minus 6, minus 3. Is that part right in the notes? The wrong notes? Yeah, I had that part right. So that was just a typo with minus 9. Okay, I've got 2 different ones. So what do I do with that information? I've got 2 different ones over here. What do I do when I have 2 different possible values of m in a linear differential system? I add them together. So I've got 2 different things that would solve this system. I've got 2 different pieces of this. So I had better write it like this. 2 here, whatever, C and D, minus 3 times time. So I've got this guy, this guy. My x is a combination of both parts. My y is a combination of both parts. My x over here is a combination of the p and the q. My y is a combination of the p and the q. The p part here is the solution for the first eigenvalue. The q over here is the solution for the second eigenvalue.
so just taking a step back, we were trying to solve that coupled differential equation, right?
Yeah.
And then when we were talking about the uncoupling needing two first order ones, that was something separate, correct? That wasn't the same one.
It's not the same problem. We did it more straightforwardly, but effectively what we did was we went through, and this Kramer's rule trick was playing the game of doing the eigenvalue decomposition for us. And when we come back to here, it's the same as if we had done it that way. These are, because the linear algebra piece, we had to solve these two algebraic equations. And we solved them by uncoupling them, which meant that we had a Kramer's rule constraint, which is the same thing as what's happening over there. So it is the same. We walked through them a little differently, but it ends up being the same thing. I could have also just plugged in and found my P and my Q, and my P would have been this one, and my Q would have been this one, and then I would have gone off the other way. So it's the same linear algebra in both cases. Okay? So one quick thing before we go. Let's quickly draw what we think that figure looks like. Okay. We are in an XY space. Y, X. Where's our fixed point? 0. If I am on this branch, I'm exploding away. If I'm on this branch, I'm collapsing in. Oh, I haven't written it in a way that's easy to see this. D. Let me see. I'm going to cheat a little and draw what the answer looks like. So this direction is the collapsing in direction, which is the -3 direction. This direction is the blowing out direction, which is the +2 direction. And the in-betweens are combinations. So here's my fixed point, and in this case it's sort of half stable. It's coming in from this direction, it's going out in that direction, it's coming in from this direction, it's going out. It's like 1/4 stable. You can color it like that. And this collapsing direction is what is coming from this part of the solution. This exploding direction that's coming from this part of the solution. The orientation of this line is the orientation of the P eigenvector. The orientation of this line is the orientation of the Q eigenvector. So the eigenvector directions are telling us what the pure falling in or pure going out directions are in XY space. The eigenvalues are telling us the rate at which we go in or go out. And the mapping in between is just kind of following the flow in between. Okay, so we'll keep doing more of these on Friday until this starts to make a little more sense. So we did 2 different flavors. We did the oscillating one, and now we did one that doesn't oscillate. It either goes in or comes out, depending on where you start around that fixed point. Okay? But now all of our linear algebra needed to be there in order to get through all this stuff. Okay. So I strongly, strongly recommend that you take a look at the notes and go through some more of these examples, because we're not going to be able to do all of the examples I have in the notes of these classes of solutions, but they're going to be important flavors of that. And we're going to want to be able to draw these kind of diagrams quickly without going through all of the derivation side. Which is what we're going to work on next time.